Okay, welcome to Robotics 1. We will continue our discussion on homogeneous transformations. And in today's class, I'm going to work out some tricky problems. So why do I call these tricky problems? Because they are not satisfying all the four rules that we discussed in last class. So let me start with this problem, wherein you have a revolute joint. Then you have another revolute joint. So you have one revolute joint, you have one more revolute joint, and at the end of this revolute joint, you have a prismatic joint. So in this problem, and the prismatic joint, the joint direction is something like this. So let's identify the first revolute joint, second revolute joint, and the third joint is prismatic joint. If you look at this robot, you have the first revolute joint, which is perpendicular to second revolute joint. And then what you have is you have a parallel prismatic joint. Now what we need to do is we have to follow the process and try to find out the coordinate system and their direction. Remember the rules. The first rule is your z-axis has to go through the joint variable. So this is going to be my 0th frame. This is my z0. Then I have z1. And since this is a prismatic joint, I'm going to have my z2 here. And I'm going to, just for the sake of simplicity, I'm going to call this point as end effector, and I will assign a coordinate system to the end effector, which is similar to the coordinate system on the prismatic joint. Next, I will have x0. Please understand, the direction of x0 does not matter because there is no frame before the 0th frame. However, direction of x1 matters because you have a frame before the first frame. So now in this case, x1 needs to intersect z1 and z0, and then x1 has to be perpendicular to z1 and z0. So this, in this case, this gets satisfied. Now the question is, what do we do with x2? And this is an important question. I want you to understand what is happening here. In theory, we have two possible locations for x2. Two possible locations of x2, and I will try to show it in the three-dimensional plane. So x2 could be along this axis, x2 could be along in this direction, x2 could be going up, x2 could be going in the bottom direction. So we don't know what, so let's try to see if I were to use, and this is just an exercise, and I'm gonna do this just for one problem. So think about it. If I place my x2 somewhere here, x2 is perpendicular to z2, x2 is not perpendicular to z1. Do you agree with me? Which means this is not an ideal situation. Same thing if I decide to have x2 in this direction, that again is not satisfying the four conditions. So what I'm going to do is I am going to use x2 just for the sake of discussion, maybe in this direction. Now that solves two cases, but not one. So check this out. I want my x2 to be perpendicular to z2. I want my x2 to be perpendicular to z1. So in this particular configuration, please note, and I have to write this down, x2 is perpendicular to z1 and z2. However, x2 is not intersecting z1, and this is a big issue. x2 not intersecting z1, which means somehow we don't know here what to do. But let's move on. For the time being, what we should try to do is we should try to satisfy maximum conditions possible. So in this case, even though all three conditions are not getting satisfied, and they are x2 has to be perpendicular to z1, x2 has to be perpendicular to z2, and x2 has to intersect z2 and z1. So out of these four, three conditions are satisfied. So what I'm going to do is I'm going to stick to this convention for the time being. So let's assume again for end effector, always remember the coordinate system of the end effector. It's easier if it is aligned with the coordinate system of the joint before the end effector. That always helps. So I'm going to state Z3 and X3 like this. And let's complete the triad by the right hand coordinate system. Once again, fold your fingers. Thumb is your X, pointer is your Y, and middle finger is your Z. And now you can twist and turn your hands, actually the right hand, not both hands, just right hand. And then you will agree with me, or you can correct me if I'm making a mistake. This is going to be my Y naught, XZ. This is going to be my Y1, and ZX, this is going to be my Y2, and this is going to be my Y3. Everyone clear with this? Any questions here? Yeah. So I understand why the R is perpendicular, but why is the perpendicular to R? Which is, sorry, say that one more time. So it's R perpendicular to R parallel to P. Yeah, P. Oh, okay. P is perpendicular. You're right. Oh, so you're talking about this. Okay. Yeah. And you're right in the sense that what you need to do is you have to look at the direction of Z0, direction of Z1, and direction of Z2. Since Z0 is perpendicular to Z1 and Z1 is perpendicular to Z2, this is R perpendicular to R perpendicular to P. Okay, any other questions? Intersecting and perpendicular. Intersecting means it needs to cross, and perpendicular means it needs to cross at 90 degrees. Two axes could be perpendicular to each other, but not intersecting. So the another question I see on the board is, how do you know which rules to break? Hey, try to do your best. Try to get as many rules satisfied as possible. If none of the rules get satisfied, there are tricks that we can do. But just to start with, try to satisfy as many rules as possible. Okay. Then the next thing is, let me copy this whole thing. So, because I'm gonna need this later today. Okay. So let's start with the first joint, and the first joint is 0R1. So 0R1. This joint, I'm gonna assign the angles theta 1, theta 2, and usually the extension of the prismatic joint is defined in terms of D. So I'm gonna call this D2. Now there are some fixed distances. So I'm gonna specify those fixed distances, something like this. So the distance here, I'm gonna call this as A2. The distance here, I'm gonna call this distance as, I'm sorry, let me call this distance A1. A1. This distance as A2. And then what I can do is I can call this distance as A4. So, and again, just a quick note about the convention. Even though our frame is 0, our the variables are theta 1 and A1. Our frame, if it's 1, our axes are x1, y1, z1. Our angular variable is theta 2, and the distance variable is A2. And when we go to the next frame, which is y2, z2, x2, please note our extension variable is D3, and that D3 variable is going to change. And last, we have A4. And again, this is just a convention that is used in robotics textbook. You can use or name different variables. Your answer would still be the same. Okay, so now let's start with 0R1. Please note the rotation is about Z0 and the rotation is positive. Curl your fingers in the direction of the rotation. Thumb is aligned with the Z axis. So the rotation is positive, which means my rotation matrix is going to be cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1. 0, 0, 0, 0, 1. And what I need to do is I need to multiply this with the projection matrix x0, y0, z0, x1, y1, z1. So projection of x1 onto x0 is 1. Projection of y1 onto z0 is 1. And projection of z1 onto y0 is minus 1. So which means I'm gonna take a shortcut here, and I hope you will follow this. I'm gonna multiply these rotation matrices and write down the resultant rotation matrix in the 3x3 matrix, 3x3 matrix of the homogeneous transformation. So first row, first column, that gives me cosine theta 1. First row, second column, that gives me 0. First row, third column, that gives me sine theta 1. Second row, first column, that gives me sine theta 1. Second row, second column, that gives me 0. Second row, third column, that gives me minus cosine theta 1. Third row, first column, I get 0. Third row, second column, I get 0. Third row, third column, third row, second column, I get 1. And third row, third column, I get 0. And I just want you to note that 1 appears in the column or rows where there is no sine or cosine. So in case if you make a mistake in multiplication, that should be your sanity check, that this number 1 has to appear, and along the row and the column of 1, there should not be a sine or cosine term. The next thing is 0, 0, 0, and we have 1. The last but not least, for the positions, I'm interested in the distances between these two frames along x0, y0, and z0. Along x0, the distances between the frames is 0. Along the y0, the distance between the frames is 0. But along z0, distance between the frame is a1. And I want you to be super aware of the fact that the direction cosines or the vectors that you would be considering are along x naught, y naught, and z naught. So we don't care if the distance along with z naught is in the distance along y1, but you don't have to consider y1. Always this is the 0th or the previous frame. So note this.
I have a question.
Yes.
So, I mean, isn't x0 and x1 also a1 distance away? Like, I'm just picturing the x0 plane and x1 plane, and they're a1 distance apart.
Is this still going on? It's awfully silent now.
I think it's coming back.
I think we lost him.
Crickets.
Hello?
Did you guys hear my question?
Yes, I did.
Yeah.
Yeah.
The reason why is because A1 is going in the z direction, so it only represents the value of z going up, right? So imagine that the if you look at another one that does have it
Oh.
Okay, can you hear me?
Yeah.
Yeah. All right. So, yeah, I will give you time to discuss the problem among yourself after the class, but let me please answer the question and move on to the next stuff. So the answer to that question is the distance between the 0th frame and the first frame is along z naught, not along x naught or y naught. Understood?
Yes.
Cool. Now, what I need to do now is I need to do 1 R2. And 1 R2, once again, the rotation is about Z1. Theta 2 is positive. So I have cosine theta 2 minus sine theta 2, 0. Sine theta 2, cosine theta 2, 0. 0, 0, 1. The next thing is I need to multiply this by the projection vectors x1, y1, z1, x2, y2, z2. Now, if you look at the projection of x2 onto y1, it's 1. Projection of x2 on x1 and z1 is 0. Projection of y2 onto z1 is 1. Projection of z2 onto x1 is 1. Okay, all is good and great, but here is the fundamental problem. Frame number 2, and this is an important problem, and I want you to recognize this. That's why I'm going to circle these two frames. Recognize frame 1 and frame 2 do not satisfy all the 4 conditions. So what I'm going to do is, in my mind, I'm going to translate, and this is super important, I'm going to translate frame x2 onto x1. So I'm going to translate frame x2 onto x1. And I'm going to show my frame x2 superimposed on frame x1, something like this. And I will draw this figure again, but I want you to understand. And so what I have done is, since the frame was not satisfying the 4 conditions, what I did, I had the first frame, and I'm going to draw this frame again. This frame is x1, y1, z1, and I have another frame which is x2, z2, and y2. I'm going to translate this frame on to the frame number 1. So frame 2 needs to be translated onto frame number 1. And why is that needs to happen? The reason it needs to happen, because right now these 2 frames are not satisfying 4 conditions. But recognize, as soon as I translate frame number 2 onto frame number 1, all the 4 conditions get satisfied. Do you agree with me? What was the condition that was not satisfied? The condition that was not satisfied is x2 is not intersecting z1. This condition was not satisfied. But as soon as I translate the frame, I could satisfy this condition. So now, when I translate the frame, and I'm going to show you the translated frame here. So this is x2, this is z2, and this frame is y2. Do you agree with me that all the 4 conditions are now satisfied? In other words, x2 is now perpendicular to z1, x2 is now perpendicular to z2, and x2 is intersecting z1 and z2. Before I proceed further, I just want to make sure everyone understood this transformation. And why did we do this? Because the 4 conditions were not satisfied. Now I want you to take a moment and look at the projection matrix that we just derived. Does projection matrix, and when I say projection matrix, I want you to look at this matrix. Does this projection matrix change? This projection matrix does not change when we translate the frame. Do you agree with me? Check this out. X2 is still in the direction of Y1. Y2 is still in the direction of Z1. Z2 is still in the direction of X1. Everyone understood? The projection matrix does not change. What changes are the distances, and I will get to that in just a second. Let me perform this multiplication and find out the final matrix. First row, first column, that gives me sine theta 2. First row, second column gives me 0. First row, third column gives me cosine theta 2. Second row, first column gives me cosine theta 2. Second row, second column, that gives me 0. Second row, third column gives me sine theta 2. Third row, first column gives me 0, 1, and 0. Are you with me so far? So this is my rotation matrix. Now, this is half the battle. Please note, we have not derived the homogeneous transformation. But for homogeneous transformation, one key important piece is the distance between two frames. Now, please understand, when frame number 1 was away from frame number 2, when frame number 1 was away from frame number 2, the distance between these two was maybe A2. So when they were away from each other, this distance was A2. But since we have translated, the distance between frame 2 and frame 1 is going to be 0. And I will write this again. So when frame, and this is super important, when frame 2 is translated to frame 1, the relative distance between translated frame 2 and frame 1 is 0. What that means is, if I want to draw the homogeneous transformation, and this is a super critical part, and I want you to be very, very aware of this. For the practical purposes, to solve this problem, you should consider that frame 2 is aligned with frame 1. So this is going to be your Z2, this is going to be your X2, and this is going to be your Y2. And I'm going to just call this frame X bar, Y bar, and Z bar. Now, when I write down the homogeneous transformation matrix, and this is important, when I write down the homogeneous transformation matrix, I should be deriving the homogeneous transformation matrix considering this translated frame. So that's going to be 1H2. And if you look at 1H2, you're going to have a 3×3 rotation matrix. And that 3×3 rotation matrix is sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0, 0, 0, 0. You will have 1 here. And please note the relative distances between the translated frame 2 and the original frame 1, they are zeros. So you will have 0 here, 0 here, 0 here. So now the question is, some of you may ask me, wait a second, then what happened? What really happened to the distance, which is A2. So what really happened to this distance A2? Now, no need to worry about it. There are two ways to explain. What I want you to understand is the way we derive this rotational matrix. We have taken care of the relative orientations of frame 2 and frame 1, which means I could directly go to frame 3. And please understand, you have a prismatic joint in between. It is super important. Between frame, and I need to write this, between frame 2 and frame 3. And when I say frame 2, I mean this frame. And when I say frame 3, I mean this frame. Between frame 2 and frame 3, we have a prismatic joint. It's not a revolute joint. So we have a prismatic joint, which means there is no change in the orientation, no orientation change. The only thing that would change is the relative distance. What it means is, I will go ahead and derive this. So check this out. So if I were to write down something like this, let's do this exercise. If I were to write down R23, so which means the rotation between frame 3 and frame 2. There is no rotation between frame 3 and frame 2. Why? Because there is no revolute joint. It's just a prismatic joint. And that means your rotation matrix is going to be identity. So since it's a prismatic joint, no rotation due to P, which means there is no R, just P. However, what happens, and even though this may seem like a trivial exercise, I want you to do this. What happens with the projections? X2, Y2, Z2, X3, Y3, Z3. X3 is aligned with X2. Y3 is aligned with Y2. And Z3 is aligned with Z2. So again, what you have is, you have two identity matrices multiplying each other, which means in your homogeneous transformation, the first 3 by 3 matrix will remain an identity matrix. So what I'm going to do is, I'm going to write down 2H3. And if I write 2H3, the matrix going to be 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then here there will be 0, 0, 0. And here there will be 1. I left a space for a reason, because now let's consider what is happening. Distance, I'm interested in finding out the distance between the old the X3 and the translated X2. So this is the distance I should be considering. So I'm gonna show you that this is the distance that should be used here. So this is the distance. So the distance between the translated X2, and I need to write this down. So here you will have distance between translated frame 2 and frame 3 along x2, y2, z2. So I will have x2, y2, and z2. Now let's take a look at it. If the joint variable, and I need to be, let's specify this is a4. So this distance is a4. So can you see that the distance between these two frames is something like a2, and I want you to focus on the green arrow, is a2 plus d plus a4. So this distance is d and this distance is a4. Are you with me? The distance between these two frames is a2 plus d plus a4. Two things to note. d4 is a joint variable. I mean, so actually let me write this down here. I said this is d, just to be considered d3. Okay, d3 is a joint variable. So this guy is a joint variable. What do I mean by joint variable? Which means it changes. So d3 is going to change. a2 and a4 are going to remain constant. Everyone understood this? So d3 could change. a2 and a4 will remain constant. But think about the rotation theta 2. If the rotation is theta 2, when theta 2, and I want you to note where is theta 2? Theta 2 is here. If rotation theta 2 is equal to 0, then along x1, it would be a2 plus d3 plus a4. But for a non-zero rotation, of theta 2, your equation is going to look like, and wait for it, for a non-zero rotation, that is gonna look like a2 plus d2 plus a4 cosine theta 2, a2 plus d2 plus a4 sine theta 2, and here it will be 0. So I want you to note that there is a cosine theta 2 and a sine theta 2. And just note that there is an error in solution of problem 3 in Canvas. And that error is deliberate, because I want you to notice that if you, in that solution, I did not add cosine theta 2 and sine theta 2, but that is super important. So 1h2, why isn't the distance a2? Okay, 1h2, why isn't the distance a2 in x1 direction? Okay, the reason is not in x1 direction because the frame is translated to frame 1, and the relative distance between the translated frame 2 and frame 1 is 0. Everyone understands? Yeah. Now let's think about it. If you have a revolute joint along with the prismatic joint, just imagine that joint number 2 has rotated by some angle theta 2. And then what would happen? The prismatic joint also will get rotated. What that means is, if at that point the prismatic joint extends, which means you have some non-zero D3, you are going to have a component of D3 along X1, a component of D3 along Y1. And that is the reason why you will have to take A2 plus A4 plus D3 together. If prismatic was revolute, that is apples to bananas. Let's look at it later. This problem is confusing already. So yes. Okay, so if you think about, I want for a moment, I want you to look at the green arrow that I have drawn between the frame 1 and frame 2. Rotate by angle theta 2. So what would happen? What would happen is you are going to have a y direction component and an x direction component. Oh, yeah. Okay. You are right in a sense. You are right in a sense. I made a mistake here. You are right. Okay. It should be with respect to y2. So which means this will be cosine. Okay. You are absolutely right. Okay. You're absolutely right. So I will just rewrite this. So please note, this distance is along x2, this distance is along y2, and this distance is along z2. So let's look at x2, y2, and z2. So the distance between these frames along y2 is 0. The distance between these two frames along z2 is A2 plus D3 plus A4 cosine theta 2. Yeah, I made a mistake, and thanks for catching that. And this distance, because please note, the frame that I'm referring to, and I'm going to show that frame, is this. Not x1, y1, z1. So along x2, it is going to be A2 plus D3 plus A4 sine theta 2. Are we good? Does it make sense? All right. I know this problem is a little confusing. So what I'm going to do is I will try to explain this problem again, because believe you me that you will have the same issue with the homework problem. So in this particular problem, we have a revolute joint perpendicular to other revolute joint, perpendicular to other prismatic joint. We initially set up the coordinate system, and then what we did is we tried to find out the rotation matrices. For the first joint, for theta 1, which is 0R1, we do not have any problem. That is simple. However, if you look at frame 2, our 4 conditions are not getting satisfied. Out of 4 conditions, 1 condition is getting violated. So let me answer this question. How do we know which condition to allow violation and which condition to maintain? At the end of the day, before you write a forward kinematics equation using the technique that I have shown you here, the homogeneous transformation, all the 4 conditions must be satisfied. And the way you can satisfy those 4 conditions is by translating the frames. So at the end of the day, these 4 conditions must be satisfied. And why am I so particular about satisfying these 4 conditions? Because if you look at the textbook problem is solved using something else, which is called as Dennavit-Hartenberg parameters. Typically, in robotics textbook, that is the standard way of solving problems. But believe you me, it's a black box approach. It gives you sort of a recipe. It does not tell you the inner workings of how that approach is working, why that approach works, and in what cases that approach will give you wrong results. So I want you to follow the process that I have discussed in class, in last class and this class, to derive homogeneous transformations. And mark my words, after two more classes, I will discuss the Dennavit-Hartenberg convention, and your answers would be exactly the same. So please follow the technique that I have shown over here. Now, let me go back to the point of confusion, and this may need a little bit of thinking on your side. First and foremost, we translated the frame. This frame got translated from its original position, which was at the prismatic joint, all the way to the revolute joint. Even though that thing got translated to the revolute joint, I want you to notice when you formulate the homogeneous transformation, which is 2H3, the distances must be along X2, Y2, and Z2, because that is my base frame. My base frame is number 2. So the distances should be along X2, Y2, and Z2. When I was solving the problem before, I made a mistake and I just resolved those along X1, Y1, Z1, but that is incorrect. They should be along X2, Y2, and Z2. So I want you to look at the notes that were uploaded on problem 3 and notice that 2H3 problem, the matrix that is being derived is incorrect. The distances 2H3 on the notes for problem 3 are incorrect. So please make that correction. It's for a reason. So we know that you are not blindly following the notes, but trying to understand what is being done. Now, let me answer John's question. Does A2 is equal to 0 no matter or what we, okay. A2 is equal to 0 matters, because what happens if A2 is equal to 0? In that case, the distance between the frame 3 and frame 2, which is now aligned with frame 1, will just be D3 plus A4. Does that answer your question, John? So which means A2 is equal to 0 makes what we are doing is we are not assuming A2 is equal to 0. We are saying let A2 stay where it is, but to satisfy the 4 conditions, translate frame 2 onto frame 1. Everyone understood this? Okay, I'm gonna ask you guys one more time if there are any questions. And if there are no questions, I will go ahead and work out one more problem that will make these ideas clear. So, question? Do you have a question? Anyone question?
When you're finding the distance of 2H3, Will it be different if we didn't translate frame 2 onto frame 1?
It will be different and it will be incorrect. And the reason for that is because actually, why don't you work it out? If you work it out, you will realize that when you are in this particular case, it will just be okay. If you do not translate the frame, your distances would just be a2 sine theta 2 and a2 cosine theta 2. They will not be a2 plus b3 plus a4. Does it make sense?
All right, so in the hypothetical sense where frame 2 did satisfy all 4 conditions from the start, then we would just do d3 plus a4?
Well, that is the point, that unfortunately we are going through all this jugglery because all 4 conditions are not satisfied. If all the 4 conditions were satisfied, you don't need to translate the frame and everything will be happy and will live happily ever after.
Okay.
Okay, any other questions? This problem is super important. I don't know if I would be able to finish the next problem, but I will try. And maybe I can go a little fast because you have a homework due tonight. So you have a revolute joint. You have a prismatic joint. Prismatic joints are usually tricky. You have this prismatic joint in this direction, and there is another prismatic joint. Now, this is the first revolute joint. This is the second prismatic joint. This is the third prismatic joint. And what I'm going to do is, I'm going to give you some distances. So let's start with the convention. This is my frame 0. So this is Z0. This is my frame 1. So this is going to be my Z1. This is my frame 2. So this is going to be Z2. Next question is, I'm going to write down X0. This is going to be my X0. In this particular case, fortunately, if I were to draw X1, it is perpendicular to Z1. It is perpendicular to Z0, but unfortunately, it is not intersecting. Let's look at the last case, wherein if I were to draw X2, something like this. If I were to draw X2, something like this, then in this particular case, guess what? X2 is intersecting with Z2. X2, if you were to see the Z2, it's perpendicular and it is intersecting. So X1 is intersecting with Z1. It's perpendicular to Z1. X1 is intersecting Z0 and is perpendicular to Z0. X2 is perpendicular to Z2. X2 is perpendicular to Z1, and it's all intersecting. So all 4 conditions are satisfied. Are you with me so far? So let's identify the distances. This distance is A1. This distance, I'm just gonna say it's a joint variable D2 that changes. And this is my end effector. And this distance, so I'm gonna say this is gonna be X2. And this is going to be my Z2. And this distance is going to be A3. This is X3 and Z3. So I'm going to start with setting up the coordinate system. X, Z, Y will be something like this. X, Z, Y will be something like this. Z2, X2, Y2 will be like this. Z2, X3, Z3, Y3 will be like this. Now I can quickly write down 0 R1. The axis of rotation is theta 1. So cosine theta 1 minus sine theta 1, 0. Sine theta 1, cosine theta 1, 0, 0, 0, 1. Multiply that by a projection matrix x0, y0, z0, x1, y1, z1. Look at the projection. The projection of x1 on x0 is 1. Projection of y1 on y0 is 1. Projection of z1 on z0 is 1. And then I have zeros everywhere. So I would go ahead and quickly write down my homogeneous transformation matrix. And it would be cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1, 0, 0, 0. And now let's talk about the distances. The distance between frame 0 and frame 1 is along Z0, and that distance is A1. So this is going to be my first homogeneous transformation. Now let's look at the second case, which is 1R2. Please note 1R2 is a prismatic joint. So since it's a prismatic joint, you're going to have 1, 0, 0, 0, 1, 0, 0, 0, 1. But don't forget the projections. So projections are here to stay, which is x1, y1, z1, x2, y2, z2. Projection of x2 on y1 is 0. Projection of y2 on z1 is 1. And projection of z2 on x1 is 1. So now please note, you have an identity matrix A3. Oh yes, you're right. This would be D3. D3 are the variables that change with respect to time. A's are the variables that remain constant. So when you multiply these two, you're going to have first row, first column, 0. First row, second column, 0. First row, third column, 1. Second row, first column, 1. Second row, second column, 0. Second row, third column, 0. First row, first column, 0. Third row, second column is 1. Third row, third column is 0. So which means now my homogeneous transformation 1H2 is going to be 0, 0, 1, 1, 0, 0, 0, 1, 0. I know I'm slightly out of time, but there is no class after this. So I will finish this problem. So this becomes 0, 0, 0. Now let's talk about the distances. These distances should be along x1, y1, and z1. The distance along x1 So 1 between 1 and 2 along x1 is 0. Along y1 is 0. Along z1 is d2. And please note, I have to be very careful here. Note that z1 is going upwards. So this is the direction. So that's why it's positive. It is positive because it's aligned with the direction z1. Next thing is 2r3. Now if you look at 2r3, it's again a prismatic joint 0 0 1 0 1 0 0 0 1. But let's not forget the projections. So now you have x2 y2 z2 x3 y3 z3 and x3 on to x2 is 1, y3 onto y2 is 1, z3 onto z2 is 1. 0 0 0. So the good news is both identity matrices, identity multiplied by identity is identity. So 2h3, the homogeneous transformation is going to look like 1 0 0 0 1 0 0 0 1 0 0 0, and you're going to have 1 over here. Here you will have the distance in x2 direction, y2 direction, and z2 direction. So the direction in x2 direction, and x2 direction is this direction, the distance is 0. In y2 direction, which is this direction, it is 0. But in z2 direction, the distance is d3, and this is positive. So now if I want to find out 0h3, which is nothing but the forward kinematics problem. So forward KP, forward kinematics problem, this would just be 0h1, 1h2, and 2h3. Yes. Nope. Because the rotation is around the z. So no matter how much of rotation is about z, there is not going to be any projection on x0 and y0. So the question here is, does theta 1 affect the distance between frame 1 and frame 2? And this is a good question. I just need to write this down. Does theta 1 affect distance between frame 1 and 0? And the answer to that question is no, because the rotation is about z and the distance is also about z. So no matter how much you rotate, the x0 and y0 will rotate along with rotation theta 1, but z0 is not going to rotate. Okay, with this, you should be allowed to solve the problem. And please remember, do not follow the notes blindly. Use common sense and then make sure that the answers make sense. And finally, these multiplications can be carried out using MATLAB. So I'm going to stop here. My apologies. We got ahead by 7 minutes, but I will give you 1 or 2 minutes to ask questions, and then I will stop. Any questions?
Yeah, I was just curious. With the homework, it shows that like the coordinate system is orientated like at a 45-degree angle for one of the revolutionary joints. I was just curious if we should just make it act as a perpendicular joint.
So that's a tricky question, and again, it's good. Whenever a problem is giving you diagonal distances, don't use them. Write your own kinematic diagram, write your own frames, make sure your frames are perpendicular, because some of these robotics problem, they are set up to be solved using different techniques like screw theory or Cottonian. But whenever you have a robotics kinematics problem, derive or define your own frames, define your own distances, as long as you make sure to identify fixed distances with A and variable distances with B, you should be fine. So if somebody gives you a diagonal distance, don't use that distance while deriving the homogeneous transformation. If that distance needed to be used, we can find its component and use it later. But solve with the convention that we have discussed. Even like coordinate system, use your own coordinate system, because sometimes these problems could be defined in the left-hand coordinate system or a non-orthogonal coordinate system. We are not using those. Any other questions?